Let's do a recap of what we have discovered or learned so far. So we started with the idea of inertia and the natural state of any object, and we've gone through the details, or we have come to know that an object can either be at rest or it can be in motion, and both are valid natural states of an object. And an object that is at rest will continue to be at rest, and an object that is in motion will continue to be at motion. And that is when the inertia is unaltered or undisturbed. And as long as the inertia is untouched, the object will continue to be in its natural state. And we got to know that both are valid scenarios, and the only way you could alter the inertia is by applying some force on it, right? When you apply some force, the inertia of an object is altered, and its state can change, right? What we haven't seen or explored yet is what is the source of that force, right? And that would precisely be our focus in this video and in the next few videos. So let's get started. So the source of force, right, is what is going to be our precise focus, and in particular, we are going to explore three ideas, and those are work, the idea of work, the idea of energy, and the idea of power, right? So we'll explore these in this and the next few videos. So before we get here, before we get to understand these, let's take a scenario, right? Let's say we have a pool table or a snooker table. As you know, we have a, let me draw it properly. Let's say we have a snooker table like this. And as you might know, there'll be 4 pockets in the corners of that. And let's say we have a red ball here that we need to pocket, right? That's the target, right? We have a red ball on the table. And we have a cue stick, right? We have a stick with us, right? Now, how would we pocket this ball? So the table is at rest, the ball is at rest. How would we pocket this ball to the nearest hole or the nearest pocket, right? How do we get the ball to fall into this, to reach this pocket, right? So obviously you can use we know that, we can use the cue stick. And you're likely to place the cue stick somewhere somewhat like this, that is in line with that in line with that pocket. And if you apply some, if you move the cue stick, it is going to hit the ball, and the ball will reach the pocket, right? So that's how we have seen the game work, right? So what is actually happening, right? What is actually happening? So obviously, you see that you would keep the cue stick at a certain distance away from the ball, right? So that you can hit the ball, and then the ball reaches it. So let's take that distance to be D. Let's take that as D. Right, the distance between the end of the cue stick and the center of the ball, right? Let's take that to be D. Now, when you hit this, you know that the cue stick is going to hit the ball, and the ball is going to reach the pocket. Now, what's really happening here? By the time, right, the cue stick, everything was at rest. The cue stick was at rest, the ball was at rest, and the table was also at rest, right? So when you pushed, right, using your hands, you are probably holding the cue stick here, and using your hands when you push the cue stick experienced the force, right? Because the cue stick was also at rest, and the cue stick moved with a certain velocity before touching the ball, and that force caused the ball to reach the pocket, right? So in a sense, the cue stick has actually done some work. The cue stick has done some work to move the ball, right? So the Q stick has done some work to move the ball to the pocket, right? And the Q stick did some work because it experienced some force, right? Because everything was at rest before that, and the Q stick experienced the force because it had to move. It ended up moving from this point to this point, and that resulted in the ball moving to in hitting the ball and moving to the pocket, right? So the work done by if you were to quantify that work done by the Q stick, it is quantified as you can quantify it as work done by the Q stick is equal to the force experienced by the Q stick times the distance or the displacement, because it is moving in the straight line, both are the same, distance or displacement of the Q stick. So this is how we define work in physics. So a work done by any object or any agent, right? In this case, the Q stick is the agent. The work done by any object is defined this way: the force experienced by that agent times the displacement of that particular agent. Right? So that is how we define work in physics, in science, right? So if you were to expand this, how do you call this? So for the force experienced by the Q stick is nothing but the mass of the Q stick. So let's call the mass of the Q stick to be mc times the acceleration, right? Because the Q stick was at rest, and then when you pushed it, it moved. It acquired certain velocity, right? It moved from an initial velocity of 0 to a certain velocity before hitting the ball, right? So let's call that acceleration as AC times the distance, right, or the displacement, so which is d. Right? So this is the work done by the Q stick. So this is the formula for the work done by an agent or the Q stick, to be precise here. Right. So the work done by physics is very different from how we normally perceive work is, right? So in a practical sense, say when you are holding something, right? When I'm holding a bag, when I'm holding a bag, it's clear that because I'm doing some work, although I'm not moving. But from a physics standpoint, scientifically, I'm not doing any work, right? Because by the way we define work in science is, one of them has to be non-zero. Either the force experienced by that agent has to be non-zero times the distance. The agent there has to be a displacement. There has to be a displacement. The agent has to move a certain distance. I mean, it has to cover certain displacement, right? So if I'm just standing and holding an object, I'm obviously not moving anywhere. So my displacement is 0. So in terms of science, the work done by me is 0. Although yes, in a practical world, it is not the case, right? Because I do grow tired. Right? I cannot hold the bag for. But I cannot keep holding the bag all the time, right? But this is how we define work in science, and which is force times the displacement, and if one of them is 0, then per science the work done is actually considered 0, right? So now that we have got we have got the formula for work. Let's try to derive. Let's try to derive the unit for work, right? So we know that mass is the SI unit for mass is kilograms, and we know that the unit for acceleration is going to be so it is acceleration is velocity by time. So it is meters per second squared, right? So that is the unit for acceleration. And we know that the distance is meters, right? SI unit for distance is meters, and which means that your total your unit for work is going to be meters, kilogram meter squared per second squared. Now, 1 kilogram meter squared per second squared is considered to be 1 joule, and this is the unit. This is the SI unit for work, and 1 joule is considered to be 1 kilogram meter squared by second squared. Just like how we consider 1 Newton to be 1 kilogram meters per second, right? If I'm not wrong, yeah, 1 kilogram meters per second is what is considered as 1 Newton because of the we attribute 1 Newton for Newton's, to recognize Newton's contributions to physics and science. Similarly, for all the work done by British physicist Joule in the field of thermodynamics and electricity, we attribute the unit of work to joule, and we consider 1 joule to be 1 kilogram meter squared per second squared. So this is the unit for work. Now, if you notice, if you notice in all our any of the items that we eat or consume, anything that comes in a packet, you see that there is an energy consumption on the back of that particular product that we consume, and you see that the energy consumption is also shown as in joules. So the unit for energy is also the same, right? So which means that work and energy are actually related, and because both are having the same units, right? What we just derived as work, the unit for work is also the unit for energy. So how is that the case, right? So that's what we're going to uncover in the next few minutes. So the way we see this is, we knew that when everything was at rest, the Q stick, we pushed the Q stick. The Q stick acquired experienced a certain force, and it meant that the Q stick did some work, and by doing that work, it acquired a certain, because after doing this work, what happened? The result of this work was it hit the red ball, and the red ball would have reached the pocket, right? After doing this work, the red ball would have after doing this work and touching the ball, the red ball would have reached the pocket, which means that the Q stick acquired by doing this work, the Q stick acquired certain energy to change the inertia of this particular ball, right? That is another way to understand this whole thing. The Q stick did some work, and by virtue of doing that work, it acquired certain energy to to make the ball move, right? So to put that into perspective, movement of the Q stick is actually the work. Movement of the Q stick is actually the work done by the Q stick, and what resulted out of that? It resulted in the movement of the ball to the pocket, which means that movement of the ball. Right. Now, movement of the Q stick resulted in the movement of the ball, and movement of the Q stick is what we quantified as the work done by the Q stick, and by virtue of doing that work, the Q stick acquired that energy to result in the movement of the ball, right? So, and if you really come back, what happened? What resulted in the movement of the Q stick? It is possibly because you were holding the Q stick and you moved your hand, right? You moved your hand, and that's only then you could have moved the Q stick, right? So which means that your movement of the hand your movement of the hand resulted in the movement of the cue stick, right? And the thing here is that your movement of the hand is the work that was already done, right? You did some work with your hand, and by virtue of doing that work, you created that energy, and that energy held in the movement of the cue stick. That energy held in the movement of the cue stick, which means that the cue stick ended up doing some work, and by the virtue of the cue stick doing that work, it acquired that energy to move the ball, which means that the ball ended up doing some work, and which is about reaching the pocket here, right? So in this whole chain, you see that work and energy are just the same thing. I mean, work and energy are two sides of the same coin. By virtue of doing some work, you acquire some energy, and you need energy to do some work, right? At some point in time, I mean, we will come to how the movement of hand happens. So there must have been some energy source for us to even move our hand, right? Which we will come to in a bit. But for now, if you see here, starting from the movement of the hand, it is a chain, right? The movement of the hand does some work, which means that it, by virtue of doing that work, it generates or creates some energy. And that energy is what is used to do some other work, which was a cue stick in this case. The cue stick ended up doing that work, and that was by virtue of doing that work, the cue stick created some energy, and that's what ended up in the movement of the ball. I'm using the word creation of that energy, which is not accurate, but for now. Take it like because it's all actually related. It's the same energy that is moved from one object to the other. It is all transferred from the hand. The same energy is what is transferred from the hand to the cue stick, and from the cue stick to the ball, right? So I'm not creating anything here. The energy is just transferred through the work that is being done by the various agents, and I have three agents here. The first agent is my hand, the second agent is the cue stick, the third agent is the ball. So the same energy that originated from my hand is actually being transferred from one agent to the other through work, right? So that's how work and energy are related, right? So the last thing here is, since we are defining work as work through this formula, right, which is force times acceleration, force times displacement, and scientifically this is how we define work. So which means that work can be zero when either the force is zero or when the displacement is zero. Work can be zero. The other part is work can also be negative, right? It may not be always be positive. It can be negative, because we know that a force has in fact even force and displacement can be negative, right? Both have a direction, right, aspect to it. So displacement also has a direction aspect to it. If you consider an object moving from this point to this point as D, right? So if you consider the displacement from this point to this point as D, then you'd have to consider the movement from this point to this point as minus D, right? Same is the case with force as well. So let's take that example. Let's take an example of you have an object, you have a wooden block. Let's say you have a. Let me draw it a little straight. Okay. So let's say you have a wooden block here, and let's say there is a bullet that is that is approaching that wooden block with a high velocity. Now, what is likely going to happen after it strikes? If the block is really strong, the wooden block will pierce through this, and probably it will stop at some point if the block is fairly strong and dense, right? So it will possibly stop here. Now, if you consider this, if you consider this behavior, the uh, the work done, the work done by the bullet, right, starting from this point to this point. If you really see the work done by this particular bullet, you will see that your the bullet, just by the time if when the bullet was about to strike the wooden block, then let's consider that velocity to be u, and just by the time after it comes to a complete stop, the velocity is going to be, say, 0, right? Your final velocity v is going to be 0, right? So in this case, the bullet has undergone a negative acceleration, right? The acceleration has reduced from u to 0, whatever that speed, whatever that velocity was just before it hit the wooden block. It came down to 0, which means that the acceleration was 0. When the acceleration is 0, the force is also 0. When the acceleration is negative, the force is also going to be negative. Force is nothing but mass times acceleration, right? So in this case, the work done by this bullet at this point between, from here to here, right after hitting the bullet is actually negative, because it has come down to 0, right? Then the acceleration is negative. So this is another point that you need to be aware of, that your work can be work in science is defined as force times acceleration, which means that work in science is defined as force times displacement, and because force and displacement have a direction aspect to it, either of them can be negative, and which means that your work can be either 0, or it can be negative, or it can be positive, right? When either the force is negative or when the displacement is negative, the work done is also going to be negative. So we'll stop here, and in the next video we will talk about the different kinds of energy.
One final thing before you leave. If you wish to revise the concepts that you've just learned, please look up and try out the free Revise app bot on Telegram app. Telegram is available for free on both iPhone and Android. Also, if you did like the content that you just watched, please do like, share, and subscribe this with your friends. Thank you.